In the last week, we defined the field of complex numbers and proved that any complex field will be isomorphic to it. We also defined a metric on the complex numbers using the absolute value, which happened to be the square root of the norm function, the field norm. And we remarked that the explicit construction of the complex plane should not affect the study of analysis on the field of complex numbers. Thereafter, we studied some important topological notions on the complex plane. In this week, we will study some functions on the complex plane and some of its geometric properties. So, let's begin this lecture by discussing isometries on the field of the complex numbers. So, recall, if you have seen isometries, recall that a function f from C to itself is called an isometry. More generally, on a inner product space, we can do this. Wherever there is a norm involved, we can talk about an isometry is called an isometry if the absolute value of f of z minus f of w, this is the distance of f of z to f of w, this is equal to the absolute value of z minus w. This is the distance of z to w, and this is for all pairs z comma w in C. So basically, isometry is a function of the complex plane to itself, which preserves the distance between any 2 points. So if you look at z and w, there is a distance between z and w. Look at the image of z and w under f. Look at f of z and f of w. The distance between f of z and w, f of z and f of w is the same as the distance between z and w. If such a condition is satisfied for all points, all pair of points z and w on the complex plane, then it is called an isometry. Let us assume that our given isometry fixes the origin. Suppose f is an isometry of the complex plane which fixes origin. That means that f of 0 is equal to 0, i.e. f of 0 is equal to 0. Then let's see what happens, what is the behavior of such an isometry. The first claim in this direction would be to establish that such an isometry preserves the inner product as well. Let me make it more precise. Let f be as above. Okay, let f be an isometry on C such that f of 0 is equal to 0. The first claim is to show that then the inner product of f of z, f of w, this is equal to the inner product of z comma w for all z and w. This is a linear algebra statement to be proved. Let me not spend too much time on it. You would have probably already seen such a statement in a course on linear algebra. Nevertheless, let me just indicate a proof. The key thing to note here is that if you look at the absolute value of f of z minus f of w the whole square. So this is actually a statement which is true in general inner product space. So that's why a norm would have worked in an inner product space rather than just focusing on the complex plane. But nevertheless, this is basically the inner product of f of z minus f of w, f of z minus f of w. And I'll just immediately write it as absolute value of f of z square plus absolute value of f of w square minus 2 times the inner product of f of z, f of w. Recall that this is a real inner product space, and therefore the inner product of f of z and f of w is the same as the inner product of f of w and f of z. That's where the minus 2 has come up. And this gives that the inner product of f of z, f of w, this is equal to the absolute value of f of z square plus the absolute value of f of w square minus the absolute value of f of z minus f of w, the whole square by 2, the polarization identity as we know it. But till now we have not used the fact that f is an isometry, and we are now going to use the fact that it is indeed an isometry and that it fixes the origin. The fact that it fixes the origin tells us that f of z minus f of 0, which is 0, is the same as the absolute value of z and 0. So this is absolute value of z square plus the absolute value of w square, and this is going to be the absolute value of z minus w the whole square by 2. And by using a similar identity, this is just going to be the inner product of z and w. So in fact, I have given a complete proof of this. So f preserves the inner product. That is what we have proved. Then the next natural step would be to ask, can we say anything about the linearity of f? The answer turns out to be yes. Such a map, which is an isometry and which preserves the origin, should necessarily be a linear map. So the next claim, or maybe I'll write it down as a proposition. Let f from C to itself be an isometry such that f of 0 is equal to 0. And that way we have ensured that it is going to be preserving the inner product. The proposition states that an f is a linear map. This is first. To check that it is linear, we have to just see what happens to f of alpha z plus w. We just have to check that this is equal to alpha times f of z plus f of w. So let's look at f of alpha of z plus w minus alpha times f of z minus alpha f of w. And let's see how this behaves. So this is, again, we will use the same tricks as in the previous case. We will write this, the square of this can be written as minus alpha times f of z minus f of w with itself. This is the inner product of that element with itself. And yeah, so this is going to be the absolute value of f of alpha z plus w the whole square plus absolute value of alpha square f of z square plus absolute value of f of w square, and there will be terms involving inner product with f minus the inner product 2 times the inner product of f of alpha z plus w alpha times f of z. Maybe I should put that alpha out here. Remember, here alpha is a real number. Minus 2 times f of alpha z plus w with f of w, and there's one more term which is going to be plus alpha 2 times alpha times f of z and f of w. I hope I have not made a mistake. Yeah, but anyway, the idea is to expand out the inner product and to notice that this is an isometry and that it preserves the inner product. So this is going to be the absolute value of alpha z plus w the whole square plus mod alpha square times mod z square. Mod, when I say mod, it's the absolute value here, plus the absolute value of w square minus 2 alpha times the, or maybe I should put that in now, alpha z plus w comma alpha z, because it preserves the inner product, and I've pushed the alpha inside, minus 2 times the inner product of alpha z plus w with w plus 2 times the inner product of which one, alpha z and w. And you should check that this is exactly the expression for the inner product of alpha z plus w minus alpha z minus w with itself. So this is the absolute value of alpha z plus w minus alpha z minus w whole square. Same techniques, the same tricks involved, and you can check that this is equal to 0. But then when can be the absolute value equal to 0? We started off with an element like this, and we proved that the absolute value of that is equal to 0. And therefore, the element, the complex number itself should be 0. Hence, f of alpha z plus w is equal to alpha times f of z. plus f of w. Therefore, f is a linear map. So that's remarkable, isn't it? We started off with an arbitrary isometry and we just imposed the condition that it fixes 0. Now we have the function f to be a linear map. Actually, notice that we have not used much of the properties of the complex number as such. These are just statements and properties of general inner product space that we have used. But then we are looking at this particular inner product space and hence it's okay. All right, what next to explore? So we now know that f is a linear transformation which is an isometry, which many times I will call as a linear isometry. Any linear transformation can be described by how it acts on a basis. So let's now look at how f acts on a basis. F acts on, well, I'll fix a basis. The favorite basis of this course would be 1 and I. So let's see how it behaves on f of 1 and f of I. So notice that any element z, if z is in C, then z is a plus bi for some real numbers a and b, and then f of z, because it's linear, will just turn out to be equal to a times f of 1 plus b times f of I. So this is precisely what we are exploiting, isn't it? Okay, suppose f of 1 is equal to some complex number alpha. Oh, I am using alphas too many times. Maybe I should have used an a above, and because alphas generally are used, so I'll specify here for alpha in R. Okay, this was the case in the proof, but do not confuse in what follows. This alpha is a complex number. Alpha is some complex number. It could be a complex number which is not a real number. What can we say about alpha from the fact that f is an isometry and that f fixes origin? We know that f of 1 minus f of 0, this is going to be equal to absolute value of f of 1, and this is also going to be the absolute value of 1 minus 0, which is equal to 1. So this is going to be the absolute value of alpha. That means alpha has absolute value 1. And what can we say about complex numbers which have absolute value 1? Then alpha times alpha bar is going to be the absolute value of alpha square, which is equal to 1. Right? That's good. So now let's define m alpha bar of w to be alpha bar times w. The thing about m alpha bar is that it will also turn out to be an isometry. So notice then what is going to be m alpha bar of z minus m alpha bar of w. This is going to be equal to the absolute value of alpha bar times z minus w, which is equal to the absolute value of alpha bar, which is equal to 1. Let me not skip steps. And this is equal to the absolute value of z minus w. And therefore, m alpha bar, hence m alpha bar is a linear isometry. Notice that m alpha bar of 0 is 0. So therefore, this is going to be, like in the previous case, a linear transformation. And what can we say about the composition of linear isometries? It will again be a linear isometry. Now define T to be m alpha bar composed with f. Then T, because it's a composition of linear isometries, is linear isometry. Okay, that is good because T has some nice properties. What will be T of 1? Let's see what T of 1 is. T of 1 is going to be m alpha bar of f of 1, which is alpha bar times f of 1. But we picked alpha to be f of 1. So this is equal to alpha bar times alpha, which is equal to 1 because its absolute value of alpha square, which is 1. And therefore, T is now a linear isometry which fixes both the origin and the complex number 1. Let's see what T does to I then. Let T of I be equal to A plus Bi. And then if you look at the absolute value of T of I, this is nothing but the absolute value of T of I minus T of 0, which is the absolute value of I, which is equal to 1. That means that the absolute value of A plus Bi is equal to 1. Squaring it, we have A square plus B square is equal to 1. We also know that the absolute value of T of I minus T of 1 is the same as the absolute value of I minus 1. And we know what is the right hand side. So squaring it, let's put a square, and this is going to be the case. And T of 1 is 1. That means that A plus Bi minus 1, not. So the absolute value square is equal to 1 square plus 1 square, which is 2. 1 square plus minus 1 square, which is 2. That means that A minus 1 the whole square plus B square is 2. So there is one equation here. There is another equation here. The two equations star and star star. They give us that subtracting one from the other, we have A minus 1 the whole square minus A square is equal to 2 minus 1, which is 1. But that gives us, just solve it straight in, it will be 2A minus 2A plus 1 is equal to 1, which gives A is equal to 0. Therefore, A is supposed to be 0 here. That means B square is equal to 1, and therefore B is plus or minus 1. So T of I is either I or it is minus I. Hence, T of I is equal to, let me write it like this, either T of I is equal to I or T of I is equal to minus I. So there are only two possible options for how T will behave. Therefore, check that T of A plus Bi is either A plus Bi or A minus Bi. So either T of Z is equal to Z or T of Z is equal to the conjugate, the reflection along the real line for all Z in the complex plane. So, but recall what T was. T was defined to be M alpha bar times F, composition of the isometry M alpha bar with the isometry F. And M alpha bar has some nice properties. It's just multiplication by alpha bar. If we compose M alpha bar with M alpha, we get the identity. We know the explicit inverse of what M alpha is. Notice that M alpha bar of M alpha of W, this is just alpha bar of alpha W, which is equal to the absolute value of alpha square times W, which is equal to W. Therefore, we know the explicit inverse of M alpha bar. The other way is also true, which is also equal to M alpha bar of W. And therefore, thus M alpha of T is equal to M alpha bar F, which turns out to be equal to F. So we know exactly what F is. We have recovered what F is by composing our linear map T with M alpha. We know what exactly our possibilities for the map T is. Thus, F of Z, either F of Z is equal to alpha times Z for all Z in C, or F of Z is equal to alpha times Z bar for all Z in C. So we have essentially pinpointed what the isometries of the complex plane will be if it fixes the origin. Notice that alpha is of absolute value 1. Let's do one thing. Let S1 be the set of all those functions in the complex plane such that the absolute value of z is equal to 1. Then we just notice that alpha belongs to S1. We also just faintly gave a proof of the fact that if there is any element in S1, it gives us an isometry. So if let's say Z0 belongs to S1, then define f of W to be equal to Z0 times W. Then f is an isometry. Or define f of W to be Z0 times W bar. That will also be an isometry. So the set S1 has some speciality when it comes to studying the isometries on the complex plane. S1 also is the usual familiar object. This object is what is commonly called as the unit circle. This is the set of all z in C such that z is equal to a plus bi and a square plus b square is equal to 1. We are familiar with this geometric object. It's basically, doesn't matter. So we have the axis and this will be the unit circle. So this is 1, this is I, this is minus I, and this is minus 1. And if you look at any element on the unit circle, then we can talk about an angle theta of the point with the line joining 0 and 1. This will be of length 1, and hence we know from basic trigonometry that this point will have y coordinate sine theta and x coordinate as cos theta. So this is the this will be the coordinates of the point here. It will be the same here as well. So if I am to use a different color, suppose this is in the second quadrant and suppose this angle is theta, I would suggest that you sit down and check that this is exactly going to be cos theta and sine theta again. This is going to be the case here as well. The angle, if this is theta, this is going to be cos theta sine theta, and no difference here. This angle will, if it is theta, it will be the same, cos theta I sine theta. Right, so this tempts us to use this representation somehow to describe the isometries. If you notice, so before we actually get into that, let me talk about polar representation of a complex number. Suppose z is some complex number, then you can always write z as let z and c be a non-zero complex number. Then z can always be written as the absolute value of z times, which is a positive number, times the complex number z by the absolute value of z. Let me just give them names. Let absolute value of z be equal to r and omega be equal to z by the absolute value of z. Then the first observation is that r is positive and omega belongs to S1. This is the first observation we have. The absolute value of omega will be the absolute value of z by the absolute value of z, which is equal to 1, and therefore it is in the unit circle. And the second observation is that such a representation is unique. There is no ambiguity there because R is positive. This is a unique representation. But the moment we have omega in S1, we just noticed that there is some theta. Since omega is in S1, we have omega is equal to some cos theta plus I times sin theta. We just noticed that any element on the complex plane, we will be able to do something like this. And we will use this to talk about our isometry. So, let F be an isometry which fixes the origin. Then we know that then let alpha in S1 be such that f of z is equal to alpha times z, and let alpha be equal to something cos theta plus I sin theta, let's say. Yeah, for a fixed theta, let it be cos theta plus I sin theta. Now let's see how f of so I'm now only considering those isometries which are of the type alpha times z. We could also consider and study alpha times z bar, but we'll come to that in a moment. Now, if you look at f of z, I can write it like this. It will be cos theta plus I sin theta, and z, if we write it in the polar decomposition, such a representation is unique, and it is called the polar decomposition. I didn't give the name here. The polar decomposition. Of z. So, we will look at the polar decomposition of our given element z as r times, let's say, cos phi plus I times sin phi, the variable phi. And these are all multiplication by complex numbers, and you should check that by using the basic trigonometric rules. This is cos of theta plus phi. You have to use the multiplication in the complex plane very crucially, and this will be sine of theta plus phi. So let's see, let's draw pictures again. Let's now see how this turns out geometrically. So let's draw the axis. Let's pick some vector z. So this is our z, which is equal to the magnitude. Okay, the r mod z is equal to r, and the angle here is theta. No, theta is not the angle, it's phi. This is our z. Notice that this is the z we have just drawn, and we will be looking at what is this element. This element will have the same magnitude. Notice that the r is the same, and therefore it will have the same magnitude, and it is being, it's not a straight line, yes, and this angle is basically theta plus phi, and that's happening to every z. So what we have concluded by looking at it geometrically is that it is a rotation by theta of every element. F turns out to be rotation by theta. That is the geometric description of the isometries of the type f of z is equal to alpha times z. In fact, alpha times z bar also can be described very similarly. Let's see. Now let f of z be equal to alpha times z bar. What is that? The z bar is, first, it is a reflection along the real line, and then we are rotating it. Therefore, it's going to be the description is very simple here. F turns out to be a reflection, now the reflection is not going to be along the real axis, but along a line through alpha, so through the origin. Let me just leave it at that. Notice that everything is now going to be rotated, so this will now become something like this, and this is going to be this. If this is alpha, this is our unit vector alpha, everything is going to be rotated now along by theta by multiplication when you multiply by alpha, and therefore the reflection will now be along a different line, the line being the one which goes through alpha. Basically what we have concluded is that every isometry which fixes the origin will either be a rotation or it will be a reflection along some particular line. We have given a very complete and concrete description of how the isometries on the complex plane behave. Let's now revisit and come back to the polar decomposition. That's a very important representation of a given complex number. The polar decomposition, it's a particularly useful and easy way to multiply complex numbers. Polar decomposition is easy. When multiplying complex numbers. In fact, we use this very crucially to describe the geometric meaning of our isometries. Why is that the case? If z1 be equal to r1 times cos theta 1 plus I sin theta 1, and suppose z2 is r2 times cos theta 2 and I sin theta 2, then what is going to be z1 times z2? z1 times z2 is just r1 times r2, and then it will be by a similar argument as above. This is going to be cos theta 1 plus theta 2 and I times sin theta 1 plus theta 2. So the multiplication will just be some kind of a rotation and then a dilation. That is what the geometry here says. And we saw that our isometries are multiplication by an element in the unit circle, and therefore the dilation is not there, it's just a rotation. The good thing about the isometries of the type f of z is equal to alpha times z is that if you take a loop around the origin which goes in the counterclockwise direction, the image will also be a loop which goes in the counterclockwise direction. And that is what we broadly say by saying that it preserves the orientation. It's an orientation preserving map. The reflection does the opposite. If you look at a loop around the origin which goes in the counterclockwise direction, under a reflection it will go into a loop which doesn't go in the counterclockwise direction, rather it goes in the clockwise direction. It reverses the orientation. So those are isometries which reverses the orientation. So multiplication by complex number therefore manifests as a dilation and a rotation. The polar coordinates are not very handy when it comes to adding of complex numbers. When we want to add two complex numbers, it's better to use the Euclidean coordinates. Here it will become far more complicated, but for multiplying the polar coordinates are very useful. Now let's discuss the theta and the r that comes up. If z is equal to r times sec cos theta plus I sin theta, then the r greater than 0 is uniquely fixed. Then r is called the magnitude. And cos theta plus I sin theta is also uniquely fixed. This is in S1, which is called the phase. Offset. This is of complex number. But then the theta that we are talking about, that is not necessarily uniquely fixed. So if theta in R is such that for omega in S1, omega is equal to cos theta plus I sin theta, then we say that omega is equal to, or more generally for z in S1. Z is equal to say r times cos theta plus I sin theta. Then we say that theta is an argument of z. So this is in the complex plane. So any complex number can be written as r times omega, where omega is in S1, and because of that there is a theta such that z is r cos theta plus I sin theta. Such a theta is called an argument of z. Notice that if theta is an argument, then basic trigonometric rules tell us that theta plus 2 pi is also an argument. Theta plus 2 pi k is an argument for each k in the set of integers, and that is why the word an was used. There are multiple arguments for the same real number. Let me note that if theta is an argument of z, then so is theta plus 2 pi k, where k belongs to integers. And again, basic trigonometric rules tell us that these are all the arguments. So we shall denote the arguments of z by arg of z. This. And the above remark can also be said in an algebraic manner, that this is a coset of the additive group R mod the cyclic group generated by 2 pi. So the argument can be thought of as a coset here. Geometrically, we already saw what the argument means. If you go around in the counterclockwise direction 2 pi, you get back the same number, the same vector, right? That's the geometric picture to look at. Okay, more definitions is about the standard argument. So if we pick a semi-open interval, there are multiple choices of an argument possible, as was just observed, right? It will be better, it will be good if we can have a particular interval from where we always pick the argument. So let's do one such process. If you pick a semi-open interval, if you pick the semi-open interval, say minus of pi less than theta less than or equal to pi, and demand that the argument is in this interval, is in this set, then we can talk about the argument of a complex number. Then we call the argument of a complex number, of a given complex number. Notice that we will always be able to find one argument in this interval. Such an argument is called the standard argument of Z. Is called the standard argument. And it is denoted again by arg Z, but with a capital A. Notice that this capital A Rg of Z, this is a function from C to the complex plane, and it's a continuous function at every place other than the negative real axis. If you notice, the argument here is in this manner and the argument here will be in this manner, right? So if we approach the real axis, this phi will be going closer and closer to minus pi, and if we go in this direction, the theta will be going closer and closer to pi. So on the negative real axis, there is going to be a discontinuity here. This discontinuity on the negative real axis can be shifted by considering a different semi-open interval of size 2 pi. If we are to pick 0 less than or equal to theta less than 2 pi, then what will happen is this will be what we were considering for some time. So this is going to be our theta, and again the angle is going to be like this, and the discontinuity in this case will be on the positive real axis, because if you go in this direction, theta will converge to 0, and if you go in this direction, theta will converge to 2 pi. There will be a discontinuity on the positive real axis. So there is no way of totally avoiding a discontinuity. You can shift, however, the discontinuity from one line to another. Yeah, maybe I should stop here.